In this video, we're going to talk about using L'Hopital's rule to explain end behavior and function dominance a little bit. So, for example, we might be interested in finding the right end behavior, that is, the limit as x goes to infinity of some function. And sometimes these functions can be written in a fraction form where both the numerator and the denominator are growing without bound as x approaches infinity. In other words, they both approach infinity, so that you have this form 0 or infinity over infinity. Okay, so you have the form infinity over infinity. Now, think about this a minute. As the denominator gets big, if the numerator was just staying the same, the whole fraction would go to 0. So the denominator growing has a tendency to sort of push the limit down towards 0. On the other hand, if the denominator stayed the same and the numerator was approaching infinity, then the whole thing would approach infinity. So the numerator growing has a tendency to push the limit up towards infinity. So which one wins in this sort of tug-of-war depends on which one dominates, which one grows faster. And so if the numerator grows faster than the denominator, significantly so, we say the numerator function dominates the denominator, in which case the whole thing goes to infinity. On the other hand, if the denominator function is the dominant one, then the whole thing as a limit goes to 0. And if the limit is something else, that means they're basically growing at roughly the same rate, and that's when we get some other limit besides 0 or infinity. So let's just look at just a couple of standard examples. So we're going to compare an exponential function with a power function or maybe a polynomial function. And exponential functions dominate power functions or polynomial functions. So, for example, if the power is, say, bigger than 1, both an exponential growth function, that is, and a power function that grows will be growing concave up, increasing, in the first quadrant. But what's going to happen is, the polynomial function might be above the exponential for a while, but eventually the exponential function is going to be on top of the polynomial function, and as x goes to infinity, as you go way out to the right, eventually it's going to leave the polynomial function down in the dust. And the way we can see this is by applying L'Hopital's rule. In fact, we may have to apply it several times. So if you take the limit as x goes to infinity of e to the x over x to the n, and say even with any power function where n is a positive power, both the numerator and denominator are increasing, approaching infinity, so we have form infinity over infinity, we apply L'Hopital's rule. Look what happens. The derivative of e to the x is e to the x. The derivative of x to the n is n times x to the n minus 1. Well, if that power is already a negative power at this point, then or the power is 0, so it's a constant function in the denominator, then the numerator goes to infinity, and the whole thing goes to infinity. If it's not if that's not the case, then you do L'Hopital's rule again. And eventually what's going to happen is you're going to eventually get down to a derivative linear, and you get a constant function in the denominator, or you're going to get a negative power in the denominator. Either way, the whole thing is going to go to infinity. So in particular, you can see this worked out here. If this power is a natural number, then you get the first application of L'Hopital's rule gives us e to the x over n times x to the n minus 1. When we do the derivatives again for L'Hopital's rule, because we still have the form infinity over infinity, the derivative of e to the x is again e to the x. Now in the denominator we have n times n minus 1 times x to the n minus 2. And we do it again, and we have n times n minus 1 times n minus 2. And then times x to the n minus 3. But the top just stays e to the x every time. Well, eventually the bottom, you take enough derivatives, you get down to the constant function, n times n minus 1 times n minus 2 times n minus 3, all the way down to 1. Or in other words, n factorial in the denominator. But the numerator is still e to the x. So, as we take the limit as x goes to infinity, the numerator goes to infinity, the denominator is a constant, so the overall thing is infinity. So we see that e to the x eventually grows faster than any power function, no matter how big, or even if you put a coefficient in front. So certainly that makes it grow faster than any polynomial function. On the other hand, a logarithmic function approaches infinity as x goes to infinity, but it does it slower than any positive exponent power function. So for any power n greater than 0, the limit of x to the n over ln of x has form infinity over infinity, so we apply L'Hopital's rule. The derivative of x to the n is n times x to the n minus 1. The derivative of ln of x is 1 over x. And so when you simplify that by multiplying numerator and denominator by x, you get n times x to the n. And of course, the n being a positive number makes that whole thing go to infinity. So that just gives you a couple of examples there of how we can talk about function dominance. And a couple things that you should remember are that exponential growth starts out slow, but eventually picks up speed faster and faster, eventually growing faster than any power function or any polynomial function. So eventually it's going to leave polynomial function sort of in the dust. It's going to be way up higher. And on the other hand, a logarithmic function does approach infinity as x goes to infinity. It does not approach a horizontal asymptote, but it does so slower, eventually at least, than any power function or polynomial. So for example, a logarithm is going to grow slower than, say, a square root function or a cube root function or a 100th root function for that matter.